Welcome to the video presentation of our project, CUDA support for ClangIR. ClangIR is an intermediate representation between the Clang abstract syntax tree and LLVM-IR. It is an optional intermediate step for the Clang C compiler, as shown in this diagram. It is an offshoot of MLIR, otherwise known as multi-level intermediate representation, and provides a similar service in that it gives more information about the higher-level semantics, which may enable more powerful optimization passes. The ClangIR project is currently being worked on by teams from NVIDIA, AMD, Codeplay, and Meta, which is our client. The hope is that it will one day become a useful alternative to LLVM-IR. CUDA is a widely used framework for interacting with NVIDIA GPUs. It enables you to write code to be executed on the GPU. It can be used for a wide variety of applications, most prominently machine learning applications such as large language models and computer vision. Our project was to provide CUDA support for ClangIR, which was previously entirely unimplemented. We have succeeded in this regard, and have implemented all of the core functionality, which has been subsequently accepted upstream, having been reviewed by senior engineers at Meta, and is now used in production. Our implementation enables you to compile most CUDA programs using ClangIR. To do this, we first took the Clang AST and generated the ClangIR representation. Then we performed lowering, which is the process of transforming our ClangIR into LLVM-IR. Lowering requires a registration process and rewriting function signatures to match calling conventions on different target platforms, such as MVPTX and x86. This project was technically difficult as ClangIR is a very large codebase, consisting of over 2 million lines of code, over 20,000 code files, and it takes over 2 hours to build, which meant that a lot of work and perseverance was required in order to understand the codebase structure and semantics. Here is a summarized list of our contributions. We can now compile CUDA files using ClangIR, and we will demonstrate and explain some examples now. The first example we have, called simple.cu, contains tests for different kinds of functions: device, host, and global. We will compile this twice for this demonstration, once for device and once for host. In real CUDA compilation, the device output is an object file which will be embedded into the host. This object file is known as a fat binary because it can contain the contents of many object files for different platforms. Host functions are exclusively on the CPU side, and device functions are exclusively on the GPU side. Global functions are implemented on the GPU side and called from the CPU side. CPU side functions that are called GPU side kernels are referred to as device stubs. You can see the host and device functions in the compilation, which I will now do. I have prepared the compilation commands for each of these files. And as you can see, it has now pasted the output from CIR into these files. So this is the device output, and as you can see, it has two functions, and it makes a call to allocate an integer, double, and float in this one, called A, B, and C, and store 3 arguments in it. And in this one, it makes a call to allocate a 32-bit integer called A, and store it in that location. And as you can see, that corresponds to these two functions. Similarly, in host, we have a call to store 3 32-bit integers in A, B, and C, which is this function here. To connect host and device functions, we have to do registration to know the correspondence between host side device stubs and real device kernels. We do this by adding an attribute, cu.kernelName, which passes the device side's name to the lowering stage, where we will generate the registration function based on the name. And you'll be able to see this right here. As you can see, it's being passed as an attribute to the lower stages. The next file we have, called globalvars.cu, has tests for 3 kinds of variables: device, shared, and constant. I will now compile the 2 outputs. As you can see, it has pasted the output correctly in this file. For example, the shared variable needs to be in address space 3, which is indicated by this offload local tag, and it needs to be undefined, which is indicated by the CIR and F, and similar for the host side. Another example of a program that you can now compile due to our contributions is this one. One of our group members plan to finish off CUDA support in ClangIR over the summer as part of Google's Summer of Code. This would involve implementing improvements such as compiling host and device code in a single pass, which enables optimization across the CPU and GPU, implementing more optimizations such as more aggressive unrolling and kernel fusion, and implementing support for some non-essential features like compatibility with older CUDA versions. We had a lot of fun working on this project and hope you enjoyed this quick summary of it.